In regard to our do now, again, this is somewhat against what we talked about the other day. It says chlorine is a nonpolar covalent molecule, whereas hydrogen chloride is a polar covalent molecule. Yet, surprisingly, chlorine has a higher boiling point than that of hydrogen chloride, and we want to be able to explain why. So your approach here is to draw both compounds. You can see the nonpolar covalent chlorine gas, and we know if it's nonpolar covalent, the only type of IMF it can have is LDFs, whereas the polar covalent molecule not only has LDFs, but also has dipole-to-dipole interactions as those dipoles align in a certain manner, as we talked about yesterday. The reason why chlorine gas boils at a higher temperature than hydrogen chloride is its LDF strength, if you will, must be greater than the combination of the LDFs and dipole-to-dipole exhibited by hydrogen chloride. And that's due to the fact that chlorine gas has more electrons than hydrogen chloride. It's therefore more polarizable, and so its LDF strength is greater. The greater the strength of the IMFs, the higher the temperature required for the substance to transition from the liquid to the gaseous state. And what we're going to pick up with today, again, fits with what we've been talking about for most of this 9 weeks. This is big idea 2, and we're looking at the forces between molecules or ions today, and we're going to be focusing on these intermolecular forces. So where we left off last time is we had talked about the different intermolecular forces, LDFs, dipole-to-dipole, and hydrogen bonds, and we're going to talk a little bit about the liquid state and some liquid properties. Last time we talked about water in regard to the fact that water exhibits hydrogen bonding. We talked about this. I do have a schematic here that will help you in regard to hydrogen bonding. First thing I want you to see in regard to hydrogen bonding shown right here. Again, make sure you can identify the hydrogen bonds as we talked about last time. The other thing I want you to look at is just this short little video. I don't believe we looked at this last time. If we did, let me know. But this will show you why water expands when you freeze it.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water with 2 hydrogen atoms and 2 unshared pairs of electrons can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So you can see the hydrogen bonding, especially in ice, and how those hydrogen bonds are broken when ice melts, as well as giving rise to some of the unusual properties that water displays, which are listed here. We looked at the hydrogen bonding at high pressures. That's going to facilitate hydrogen bonding disruption. We'll take a look at phase diagrams next time, not today. You know that freshwater lakes will freeze from top to bottom. That's how the fishies can keep swimming. think I'll probably have to tell you about the time I was ice skating for the first time with my daddy, and he broke the ice and we both fell through. That was very fun. I still have nightmares about it. And again, water has a higher boiling point than what you would predict because it exhibits hydrogen bonding. We are going to pick up today with the intermolecular forces that help explain two liquid properties. We're going to be taking a look at some terms including surface tension, capillary action, what gives rise to this capillary action, and then we'll talk about viscosity. A lot of this is written out, but it's hard to just follow the words, so I've got a schematic for you to see, and I think that will help you a lot. If I poured all my water out on the bench top, it would form a little puddle where the water molecules would be somewhat arranged, and the water wouldn't completely wet the surface. That is, it wouldn't be able to spread out. And the reason for this is due to surface tension. And this is a liquid's resistance to increase its surface area. And this has a lot to do with the cohesive properties of the liquid.
Dr. Kalish, if you put, like, you know how a liquid takes the shape of its container? If you put a liquid into a vacuum where there's no, like, medium or whatever for it to take the shape of, what would you do? Or, like, in space or something. Like, well, it's just like,
You want to go try it outside and throw the water out?
no,
It might be fun.
not outside.
You
I mean,
like in outer space? You want
Yeah.
to take a trip there?
No, I mean, sure, but,
Should.
no, but, like, if there's no shape for it to take, if there's no, like, container for it to take the shape of, and it's just there, like, what does it do? Does it make little, like, balls?
I don't know. Look it up.
What happens in space?
I mean,
Look
in
it up.
actual space.
Like outer space, like in a
There's no
spaceship.
gravity.
It just floats.
So if they throw water up on the moon, what happens?
It goes like this.
Goes up.
It disperses in smaller and smaller
I've
parts.
seen
Really?
videos like that. I've seen videos of
That's so cool.
Such a step.
There you go. All right, let's take a look at some of these in action here. Oh, I've got too many things open.
Read the font.
Here we go. Here's surface tension. We're going to look at surface tension in regard to water molecules here, where there's water all around, and water as it meets air here. So here's the water molecules here. You can see this tetrahedral arrangement that they talked about, and you're going to get a resistance to increasing the surface area when the water molecules are all surrounded by others. Yep.
I found a video.
A video on throwing it in outer space?
Yeah, they just
All right, do me a favor, save the link, and we'll take a look at that.
It's literally just them playing.
If you look at the water molecules at the surface, so where water meets air, you're going to see that these will experience fewer favorable intermolecular forces than what we saw here. You don't have that fourth water molecule here. So the surface tension here versus here. You can look at surface wetting, and so this is going to differ to throwing it in outer space that some of you are clearly fascinated with. We want to look at what happens when the water hits the surface of whatever it is you're placing it on. So let's say the bench top or something. There are stronger intermolecular forces between water molecules than what you would see between the water and what it's sitting on, in this case a non-polar hydrocarbon film. And as a result, the water is going to beat up on the surface, and in order to really get the water to spread out, you'd have to smash this down, breaking a lot of those intermolecular forces.
We have like a tape, this is gonna sound weird, but we have like a tablecloth in our house that like if you pour stuff on it, it doesn't sink in the
And it's
table.
like
doesn't
Is that how
absorb
it works?
So whatever that surface is must not be terribly compatible with whatever liquid you're spilling on it, and so it's going to ball up better. So there's nothing polar in that surface.
So, if when you put it on like a table like that, it just kind of balls up because it has stronger IMFs than the table per se. That,
What you're seeing here is this is LDF only. This is LDF dip to dip and hydrogen bonds. And in order for this to hook to this, what's the only type of force it can form? LDFs, because that's the only one it has in common. So as a result, it takes a certain amount of energy to break these all up, and then it takes energy to form only LDFs, and that's not going to be favorable compared
So then
to
how would you,
all of these.
and how would you like soak up water, like with a sponge? How does that kind of happen then?
You tell me.
So like, is it because that's? It's
What do you know
water-
about a sponge in regard to its texture and its shape?
It's porous.
Yeah, and it's got a little hole, so those little water molecules can fit in there, so you're not necessarily breaking up their IMFs, but they're just sort of sitting in there. So there are holes for it to go hibernate in, if you will.
Oh.
So it's like a little cave with different places. Oh, I can shove them here, I can shove them here, I can shove them here. But yeah, there has to be some type of adhesive force between the water and the sponge. All right, so you can see the surface wetting right here, but there will be some attraction between the water molecules here and here. And you can see that wetting right there at the bottom. And then these are also responsible for meniscus formation. Shown on the left would be something like water, a polar covalent substance in a glass tube. Glass is made up of basically silicon dioxide. We'll take a look at that in a little bit. In contrast, this would be something like mercury, a nonpolar covalent substance in a glass tube. You can see this meniscus is concave, this meniscus is convex. So here the water molecules do have cohesive property, but they also have adhesive property as they stick to the sides of the glass. Think about adhesion, like a Band-Aid is adhesive. It will stick to your skin, even though the Band-Aid and your skin are made up of different properties, essentially, or have different properties. In contrast here, the cohesive forces between the mercury are much greater than the adhesive forces, and that's why you get this convex type shape. And that is essentially everything that's written here, and I like that visual. I think it helps a lot. Polar liquids do exhibit capillary action. For example, when you go to your doctor, if you still get like a little finger prick, they'll sit there with that glass capillary tube trying to get the blood to rise up. That's capillary action. It's going up through cohesive and adhesive forces. Adhesive is going to be intermolecular between two unlike molecules. Cohesive are intermolecular forces between two like forces. And you can see here the concave versus the convex meniscus. Shown here is the concave meniscus, and that's what you're most used to in the lab. The other property of a liquid that we want to mention is viscosity, and this is a measure of a liquid's resistance to flow. Substances that have high viscosity or are very viscous have very strong IMFs, or they're complex in some way. These are your really sticky things that you drizzle on your food, like honey, molasses, syrup, on pancakes, things like that. Make sure you brush your teeth well after that. Otherwise, you're going to have a mouthful of cavities. Things that are low viscosity are going to have weak IMFs like hexane, C6H14, water, ethanol, etc. So these are polar covalent substances, and they do have IMFs, but they're not very sticky. So viscosity is very much related to IMFs. The greater the IMFs, the greater the viscosity. And in baby bio, you probably made DNA, and it was very snotty, right? Think back.
We didn't do that in skills classes.
You didn't make DNA?
We made it with like Twizzlers and that was in 8th grade.
Oh.
Is it the
Oh, you didn't extract DNA from strawberries or anything?
No.
No?
Oh, too bad. Well, DNA is very, well, think about when you have a runny nose. It's snotty. That's very viscous. Don't play with that. It's gross. All right, so two properties of liquids, viscosity and surface tension. We don't see too much of this asked every once in a while, but sometimes there's a baby question on viscosity. You know, looking at these substances, this one has the greatest IMFs, which would have the greatest viscosity, the one with the greatest IMF. So if you were comparing a whole bunch of substances, you would look for the one that has the greatest IMFs and therefore in turn the greatest viscosity. Something pretty straightforward, and you'll see one of those in your practice quiz. What we really want to focus on today are the structures and types of solids, and we're going to break them up into different categories, and you're going to get a lot of practice with this in the POGL packet. They've added a few new concepts to AP Chemistry, and I'm going to make sure you're clear on those new concepts today because you'll see some baby multiple choice questions. We did see a part 2 question recently on alloys, and we can take a look at that as well. So we're going to talk about solids. The broadest categories include crystalline solids. They're going to have regular arrangement. We'll take a look. And amorphous solids. The word morph means shape. The prefix a means not. So these are shapeless. So we've got crystalline, which has a regular structure, and amorphous solids, which do not. And we can look at these structures. You can click the link right there. I've got it open here. So shown here are your crystalline solids and your amorphous solid. And I would think in 7th grade advanced science you talked a little bit about some of these rocks. I remember Earth science, you did it?
Yeah.
Okay, so I remember looking at it with my daughter in 7th grade science. Quartz, is this galena? I'm not big on rocks. I didn't take rocks for jocks. Pyrite, and this is obsidian. This is the amorphous one. So you've got your regular versus your amorphous one, and you can see this 3-dimensional structure known as a crystal lattice, and you do get these 90-degree angles here, and you can see very smooth parts on that surface there,
That's fool's gold.
which is fool's gold.
Alright.
Cool. Probably not worth much, huh?
Worth nothing.
Everything's worth something. We're going to talk about the ionic substances in regard to cleavage. We'll take a look at that in a little bit. That was asked on an AP exam recently. In regard to the 3 types of crystalline solids, they're shown in your notes here. I'm going to pull it up a little bit bigger here. And here are your 3 crystalline solids. These are examples. Diamond is a network covalent solid where you have atoms at the lattice positions. In the case of diamond, you have carbon. And diamond and graphite are both made up of carbons that are covalently linked together, but the way they're linked together differs, giving rise to very different properties for diamond and graphite. Here's sodium chloride. This is your ionic solid where you have ions at the lattice positions. Again, the structure is a crystal lattice. And here's ice, for example, where you have water molecules at the lattice positions, giving rise also to a crystalline-like structure. And these are regular solids. They have a shape.
I love when we get snowflakes in Florida.
We get snowflakes in Florida all the time.
They just don't stick.
You get snowbirds.
Yes, we do. The structure of crystals is no longer assessed on the AP exam. I didn't cross it out because you might, I don't think it's actually on SAT 2 Chem. I'm not sure. I have to go back and check.
There was a question on it.
There was? All right, so then it can be assessed, and like on a Chem Olympiad, you're not responsible for it, so we will ignore it. In terms of types of crystalline solids, again, there are different types, the main type being atomic. molecular, and then ionic, and we're going to look at each of these today. The way they differ is in terms of what is at the lattice position. For an atomic solid, you're going to have an atom at the lattice position. For example, you can have a metallic solid where you have metals at the lattice position. We're going to take a look at that delocalized non-directional covalent bonding. We're going to look at network covalent solids where you have atoms bonded to one another, and this is going to be strong directional covalent bonds. For example, diamond, quartz, graphite. Those are the main ones. We also have group 18 solids where you have noble gases attracted to one another by LDF. So those are your atomic solids, and we'll be taking a look at that. In terms of group 18 solids, one thing I do want to remind you of is if you were looking at group 18, which of the following would have the strongest IMFs, neon or xenon? Xenon. Why?
Larger number of electrons.
Has the most has more electrons, therefore it's more polarizable, hence its LDFs are stronger, giving rise to higher melting and boiling points. You got it. Good.
Dr. King,
Yep.
how would you name like a group 18 solid?
Argon.
Oh, so they wouldn't combine. Okay, I'm missing.
You can get combinations, but nothing you'd have to worry about in regard to naming.
Argon, helium.
Nah, they don't. Helium usually doesn't play with anybody because it only forms one single bond.
Radonite.
Molecular solids are another type. Here you're going to have a molecule at the lattice position. We saw that with ice, so you'd have water at the lattice position. Ionic solids are where you have ions at the lattice position. And that comparison is shown here between atomic, molecular, and ionic solids. Don't get confused with group 8A, that is group 18. That's an older nomenclature. So we've got atomic, molecular, and ionic, and we're going to take it one by one here. And at the end in your notes, I have a big chart that puts everything together for you. Questions at this point? So if you have a molecular solid, what's at your lattice position, an atom or a molecule? Molecule, all right? And if you have a network covalent solid, you're going to have an atom at the lattice position. In most cases, unless I guess you had quartz, then you could have a molecule. All right, in terms of metals, we know metals are excellent conductors of heat and electricity. Many metals can bend. They can be pulled into wires, so they have ductility. And the properties associated with metals are all linked to its non-directional bonding, in which you have a sea of mobile electrons. And I've got a great little video right here that should help.
Away from when they bond with other elements. It is ionic or molecular. Metals make up most of the elements in the periodic table, around 80%, and they are special. When metals bond with themselves, they bond in a different way from when they bond with other elements. It is ionic or molecular or covalent. It is its own metal bond. Most metals have very few electrons in their outermost energy shells, and some have vacant outer electron orbitals. What this means for the metal is that its valence electrons are decentralized and free to move around. Remember that in ionic bonds, the electrons transfer from one atom to another atom. In covalent bonds, the electrons are shared between atoms. In metal bonds, the electrons wander around and aren't transferred or shared. It's more of a communal thing where they belong to all the metal atoms around them. Metals form compact and orderly crystalline structures. They look like this. When metals are are next to each other, the valence electrons don't just stay on their own atom. They roam around the whole metal complex. They float free, as though floating through a sea of electrons, much like an individual water molecule floats free in the sea. This is why it is called the electron sea model. Each metal atom allows its electrons to roam freely, so these atoms become positively charged cations. These cations are kind of like a positively charged island and are surrounded by a sea of negatively charged electrons. It looks a bit like this. The attraction between the mobile electron and positive center is a metal bond. The electron sea model explains many of the physical properties of metals. They are good electrical conductors because the electrons flow freely in them. They are malleable because of the drifting electrons and because the cations slide easily past each other. They reflect light because of the free electrons.
You got the point. All right, so you can have that electron C model shown right here. You get these metallic cations, if you will, the positively charged nucleus with the core electrons, and then you've got this sea of positive electrons. You know the mobile electrons can conduct heat and electricity, and the metal ions can easily be moved around as you hammer it, pull it, etc. So the lattice positions would be right here, essentially the nucleus and core electrons. You've got an electron cloud where the valence electrons are found. Due to the fact that they can move around easily, you get high electrical conductivities. Group 2 metals have a higher boiling point than Group 1 metals. Why? Which has a greater sea of mobile electrons. Group 2. Explain why the melting point of metals decreases down a group. Down a group you have the same number of valence electrons, but what do you know about the valence electrons down a group? They are further from the nucleus with more electron shielding. Alrighty. So you've got your electron C model, which helps explain properties of metals. This is a new piece for AP Chem. Interesting, relatively straightforward. We did see a part 2 question on it somewhat recently. It really was pretty easy. With your metal alloys, you're going to have a mixture of typically metals, sometimes metal, and a non-metal, not as common, but you can see it. There are 2 types of metal alloys. There are substitutional alloys, and there are interstitial alloys. You probably have substitutional alloys in your house. What you find is that some of the host metal is going to be replaced by another metal that has a similar radius. They could give you a little table with metals and their radii, and you might be asked to pick which one would most likely be best suitable as a substitutional one. It's going to be the one with the similar radius. For example, brass. A lot of you probably have brass doorknobs, maybe brass fixtures, a brass knocker in your house, etc. What else?
Brass instruments.
Brass instruments. There you go. Always been. Good example. So in brass, approximately 1/3 of the copper is replaced with zinc. So you're not going to change the pattern in which the metal is oriented, and I'll show you what I mean there. Here's brass, copper, and then some of the copper has been replaced with zinc. And copper and zinc are right next to one another on the periodic table, and they are going to have similar radii. Other types of substitutional alloys include sterling silver. A lot of you probably have sterling silver jewelry. 93% silver, 7% copper, pewter, 85% tin. It also has some copper, bismuth, and antimony in it.
So more pure silver would conduct more electricity than sterling silver, right?
Why?
That conducted better.
Why?
I don't know, because I was trying to buy something and they had two different options, and the one with 99% silver, like an electronic cord.
And it said it conducted better?
Well, it was more expensive, so I assumed you'd want the one that conducted more electricity.
Yeah, you may be not comparing apples and apples. Sterling silver jewelry is probably less expensive than silver jewelry because silver is more expensive than copper.
Yeah, but I know that it would be more expensive because just silver,
Right.
more pure silver, but you wouldn't want that unless you needed it.
What were you buying?
It's like a special type of like cord for really expensive headphones.
And what was it made of?
99% silver and it has sterling silver. And the one with the
You
regular-
had a silver cord to listen to your headphones?
You can buy it.
It was silver?
Yeah.
Are you sure?
Are you sure?
Yeah, I'll show it to you.
We'll have to look into that. But in regard to your question, we got to look that up. So is conductivity of a pure metal greater than that of an alloy? I guess it depends on what you started with.
Well, it says the electrical conductivity of silver is the greatest of all metals.
Why?
That's what Wikipedia says.
Wikipedia.
Okay, Wikipedia.
Now ask why.
Why? Go ahead.
What'd you get? What'd you get?
He's still typing.
Still typing.
I put why is silver the, and the first thing was
Isn't
why is
it-
silver the best conductor?
Why is it? What'd you get?
This says the size and shape of the substance affect its conductivity. So, and silver's ion larger.
Silver's what?
It says silver's ions are larger, but that doesn't make any
Larger than
sense.
whose?
Copper, gold, aluminum, zinc, nickel, brass, bronze, iron.
Well, be
platinum.
careful with that. Silver would be larger than copper and zinc, but gold would be
Yeah.
larger than silver.
Yeah. So why does silver have the highest conductivity?
Wait, this website says that the highest conductor is copper, then aluminum, then brass, steel, bronze. Silver's not even on there.
Do you see this? That says silver.
Okay, you're on .co.com. I'm on metalsupermarkets.com. Wow.
Alrighty. Another type of alloy is an interstitial alloy. This one will make more sense in regard to strength. What you're going to see here, an interstices is a hole. So an interstice is a hole, interstices are holes, and they're going to be filled in essentially by very small atoms. So in steel, you're going to plug the holes with carbon. So essentially, steel is an interstitial alloy, and what you've got here are iron atoms in some type of regular repeating arrangement, and then these little dots here are going to be carbon, and they're going to plug in the holes, and that's why steel is so strong, because you won't get any slippage here because those holes are plugged up. And you might be asked a very simple question. It might show you a picture of this. Is it a substitutional or interstitial alloy? Why are interstitial alloys typically stronger than that of substitutional? Something pretty straightforward. But in regard to the metals, you want to understand that electron C model, and then you want to know the difference between the two types of alloys. Questions there? Go ahead. You have an answer for me?
I found it on illinois.edu.
Wonderful.
So
Go ahead.
It's reliable.
I'm ready.
It says Silver is the best conductor of both heat and electricity among metals with a thermal conduction value of about 430 W per MK, I guess. I don't know. Gold and copper both come respectively close to silver, but what?
You're the entire Chase Foster in the whole school district. You get to hear. Because I'm emailing you the link.
And it says, but it says that diamond is 5 times better conductor than silver. Like diamond's the ultimate.
Yeah, but the diamond isn't an element.
Didn't say that.
Diamond's a network covalent solid. It's very, very
Okay.
strong.
This one, Dr. Taylor says silver,
What?
HTS is like the highest conductor wire. And it says silver is the crucial element in HTS because of the ceramic core of the wire is brittle. But
See,
when-
ceramic core, and that
Yeah.
gets into network covalent too. Go ahead.
When encased in silver, the wire can be drawn out to 1/16 the diameter of human hair and can be bundled and wound for use in electric motors. So they put, like, because silver is thin but durable, they can make more of the wire within the, like, diameter that they're able to work with. So it's just that they can utilize more of the, like, of the core.
Yeah, no, I get it. Cool.
They also don't use silver this much because it oxidizes easily. So in situations where it's exposed to oxygen,
And it's less profitable than gold.
But they also wrap it and stuff, so it's not like it's exposed.
well, they would prefer to use silver and gold because it's less expensive.
Yeah, but silver is barely even considered an ore anymore because it's so unprofitable because it costs almost just as much to mine it than to sell it.
Cool. Alrighty, 2 types of alloys. We'll discuss that more later. Don't be swinging over there. Your network covalent solids, and this is what some of you started to get into a little bit. You're going to have very strong directional bonds, and you're going to get these huge networks. They're typically brittle, and they typically do not conduct heat or electricity efficiently. That's why I'm a little surprised with the ceramics comment, but we'll come back to that. One type is diamond. This is the absolute hardest. It's an insulator. Each carbon is surrounded by a tetrahedral arrangement. Let's go back and review this concept because we covered it previously, but you're going to see it in a different light here. So what you're looking at here in the left panel is diamond, and each of these is a carbon, and you'll see the carbon is covalently linked to 1, 2, 3, 4. What's the shape? Tetrahedral, SP, SP2, or SP3? SP3 arrangement for diamond.
So is diamond pure carbon?
Yes?
Okay.
But you'll see with diamond, one arrangement of the carbons. Now look at graphite. Look at that carbon. It's covalently bonded to 1, 2, 3 carbons. So that's trigonal, planar, sp2. So the way in which the carbons are arranged give rise to very different structures. Diamond, graphite. Graphite is used to grease things up. Like I had a stair stepper when I lived in Baltimore. It was squeaky, so I got some liquid graphite. I greased up the pistons, and then it was nice and quiet, and my neighbor stopped complaining. Diamonds, definitely a girl's best friend. Haven't messed up my little diamond here. My husband would get mad at me.
Is cubic zirconia called that because of its structure? Like cubic?
It's cubic.
Like, does it have a like special structure?
Does it look like that?
Yeah.
That's a good question.
Oh, jeez.
Get busy.
Cubic.
That's right. We can keep track of all of them because we're going to have lots of problem solving time, so we can look up all this stuff. So you can see the different arrangement between diamond, tetrahedral, sp3.
It looks like that.
In order to scratch a diamond, is it tetrahedral?
I'll find out.
Well, look at it. Is it attached to 4 other atoms?
No.
That's why it's not as good as a diamond. And boys, don't try and pull one over. All right. So to scratch a diamond, you have to break a lot of covalent bonds. Diamonds have a ridiculously high melting point, and you'll see that with your network covalent solids. They will have the highest melting points of all. Yeah, that's what I thought.
It is touching.
So graphite, again, is slippery, black. It's a conductor, whereas most are going to be insulators. But graphite is a little bit different. You get these 6-membered hexagonal rings that link together. You get 6 of them. And then they lie in planes, and there's weak bonding between the layers that allows for slippage, and that's why they're good at greasing things up. Those electrons are delocalized throughout the different regions here, and so that's what's going to allow for slippage, gliding, lubrication, etc. Here's buckyball, where you have 60 carbons linked together in this soccer ball-like arrangement, and there are other types of carbon fullerenes. You can have C70, etc. So you've got diamond, graphite, and buckyball as examples of carbon containing network covalent solids. You can have silicon containing, for example, silicon is found in compounds that make up the Earth's crust. Silica, shown right here, silicon dioxide. And there's a key difference between carbon dioxide and silicon dioxide. And you know carbon dioxide is a nonpolar covalent substance where you've got double bond between the O and the C. So you have pi bonding. With silicon dioxide, you don't have that pi bonding arrangement. And silicon dioxide is going to make up quartz and sand. Quartz is an excellent example of a network covalent structure. We're going to look at this network of SiO4 tetrahedra. We can take a look at that. Uh-oh, that's not right. This looks like it's only in your book. I don't seem to have a, what do you call it, of it, but I'll find it. This is actually the newer edition, but your old edition is hiding under the iPad.
Did you know that ruby and sapphire are the same stone?
Yep.
Why would silica have network bonds when network bonds are a type of atomic bonds and silica has a
Yeah, and you know, that came up before too, because you really think of that more like a molecule than an atom. And that's a good question, because in the Pogel packet, they talk about what's at the lattice position, and to me this is more molecular in nature. So that is a good question. I don't know. We better research that too. Let's write that down. I have so much work to do the second half. I can't wait.
This video is going to be absolute, like, garbage.
I wanted you to see this tetrahedra-like arrangement, but again, you can see that right here. And you can see, for example, here what it looks like. And this also is in your Pogel packet. I don't really have a simple one. This one's not bad, that whole network right there. But that's what gives rise to quartz and other substances that contain silica. What's really kind of cool is when you heat silica above its melting point and then you cool it quickly, you get glass, which is an example of an amorphous solid. And that's going to be polar covalent in nature, and so you could get those types of properties between water and glass that we talked about. And then this was the other piece, because you mentioned ceramics. Typically ceramics are made from clay, and clay does contain these silicates. And you've all at some point or another made something that you fired in a kiln and tried to give to your mommy as a present, and she said it was beautiful. Yeah.
It exploded.
Yours exploded?
Yeah.
Nice.
Well, okay,
Look at
so
the air.
my
So did your mommy get a present?
So I made
Oh,
the real
no.
one. I made the real project, and then the art teacher was like, "Faith, everybody else is still like making theirs, so you can just make whatever with the clay." And I tried to make a little clay elephant, but because the body was so dense, it exploded.
Oops.
Great stories.
All right. So network covalent solids you want to be familiar with, and this is really getting laundry list, and you'll see at the end I've got a table for you that I think will really help you. So diamond, graphite, buckyball, silicas, quartz is the one that they typically ask about, all examples of network covalent solids. The other piece in this section I want to mention, and this often is a multiple choice question, are your semiconductors. Semiconductors are, of course, along the stair-step line. For example, if you look at a periodic table, your semiconductors, your metalloids are going to be boron, silicon, germanium, arsenic, antimony, tellurium, astatine. These are considered metals here. And these are semiconductors, and they're not going to conduct electricity as well as metals, but they will conduct better than nonmetals. But you can enhance conductivity of a metalloid by doping it. And the way you dope it, you dope it. You dope it either by replacing the metalloid with an element that contains more valence electrons or with an element that contains fewer valence electrons. When you dope it with an element that contains more valence electrons, you get an N-type conductor, N for negative. For example, if you look at a periodic table, here is silicon. If you dope it with arsenic, silicon has 4 valence electrons, arsenic has 5. So the addition of a valence electron results in an N-type conductor. If you dope it with an element that contains fewer valence electrons, such as boron, then you get a P-type conductor. And this will enhance conductivity. So the question's going to be something very easy. Which of the following would be an N-type conductor? And you'd look for the one that contains more valence electrons. And you can see that shown right here. Silicon doped with arsenic, an N-type. Here's the negative red charge right there. A P-type, you replace it with something that has fewer valence electrons. Here is the positive hole, if you will, and it is the positive hole that's the charge carrier. For those of you who go on to physics, you'll talk about circuits and you'll talk about these PN junctions. We're not going there. So you do want to know the difference between N-type and P-type. You'll definitely see a very simple multiple choice question on it. Don't foresee any difficulty with it. The last two types of solids we want to mention, and again, you're going to have a lot of practice time with this in the POGO packet. It's really going to take it apart nicely for you. Molecular solids, this is when you have a molecule at the lattice position. These are going to be strong covalent bonds within the molecule, but weak IMFs between them. We've already talked about these. For example, nonpolar substances have LDFs only. Polar substances have dipole-to-dipole forces and LDFs, and some have hydrogen bonding capability. Ice would be an example that contains all 3 IMFs. Carbon dioxide, a nonpolar substance, what type of IMF would it have only? LDF. S8 and P4 also nonpolar, so they only have LDFs. So we've already talked about the molecular solids. The last thing we want to mention briefly before you have time to really practice this is going to be your ionic solids. With your ionic solids, these are very stable. These have much higher melting points than what you see with your molecular substances. Network covalent will be the highest, but ionic will be higher than covalent. You have strong electrostatic forces. and these forces are known as inter-ionic interaction. And you'll see that each ion will be attracted simultaneously to several ions of the opposite charge, and we'll take a look at that. In terms of ionic solids, what helps explain their very high melting and boiling points is their lattice energy, and we talked about coulombic attraction previously. You'll recall, or should recall, that force is equal to the magnitude of the positive times the magnitude of the negative charge over r squared. So the greater the charge, the greater the force. If the charge comparison is the same, you look at the radius. So why would magnesium oxide have a higher lattice enthalpy than sodium chloride? Charge here is 2 plus, 2 minus, so 4, 1 plus, 1 minus, so 1. So this has greater charge, hence greater coulombic attraction. And the link here is with the greatest lattice enthalpy, it will have a higher melting point. And you can see that comparison here. So the greater the lattice enthalpy, the greater the melting point, because the interionic interactions will be greater with greater lattice enthalpy. And that's the key here, and that's written out here as well. As the charges increase, you're going to get greater lattice enthalpy. As the radius decreases, you'll get greater lattice enthalpy and a higher melting point. Now, ionic solids don't conduct electricity. How come?
But salt water condenses better than water.
That's, well, be careful here. So in ionic solids such as sodium chloride spilled out all over the tabletop will not conduct electricity. Is an ionic solid comprised of ions? Yes. Can the ions move freely? No. In order to conduct electricity, it must be comprised of ions, and the ions have to be able to move freely. In a solid, the ions are in a fixed position, so they won't move freely. But when you dissolve the salt water in water, you break these interionic interactions, and now the ions can do what? Move freely, and therefore you can conduct electricity. So ionic solids don't conduct electricity, but solutions of ionic solids are excellent conductors of electricity. I'm going to throw this cleavage piece at the end. And we'll take a look at that. It says arrange the following ionic solids in the expected order of increasing melting point. So what are you going to consider here? You're going to consider mobile electrons, or are you going to consider lattice enthalpy? Mobile electrons are for metals. These are ionic substances. So for ionic substances, which has the greatest lattice enthalpy? It's got to be this one with a 2 plus and 1 minus. These are all 1 plus, 1 minus. So this is the greatest. Looking at these, you've got to look at radius. The greater the radius, the weaker the lattice enthalpy. So if you consider this one, the radii of these two ions are going to be greater than these, and cesium is going to have a greater radius than potassium ion. So this has the greatest radius and therefore the weakest. So that's going to have the lowest melting point. If you're comparing these two, which ion has a greater radius, chloride or iodide? Iodide. So that will be second weakest. So first weakest, second weakest, then that one, then that one. And the last thing I want to mention to you, this came up on an AP exam too. I'm going to go to a certain spot in the video. I marked the time. I want you to look at how ionic substances break. There was a funky little diagram one year, and I want you to be familiar with it. For those of you who were with me in honors, you would have seen this previously, but I'm not sure it's stuck, so I want to just take a minute to show you.
Dr. K.
Huh?
If you go to 228, like where you said,
Uh-huh.
and if you just right click, you can copy the link with the time in it.
Oh, yeah?
Yeah, go to 228.
Just done it now.
Oh, I couldn't see it. Yeah. And like right click on there, copy video URL at current time.
Ah, thank you. So I don't need my little,
Yeah.
I should just replace this?
And then go to 228 part.
Well, I don't know if I want to replace this, just in case it gets messed up. Let's see if it worked. How cool! Learn something new every day. Thank you so much. Except it didn't go anywhere.
Loading.
Nope, my word just crashed and burned. All right, let's go to the videotape.
Oh yeah. Yeah, I call it tonight.
All right, so here's your lattice structure with pluses and minuses, and now you're going to apply a force. You're going to smack it. Ready?
Latin
We have
structure.
anions and cations alternating regular lattice structure. Remember the lattice structure is normally three-dimensional. Well, it is three-dimensional. But I've just represented it here two-dimensionally to explain what happens when a force is applied. So here's my force, and it pushes. And what happens here is that the like charges align to one another, and that causes those like charges to repel one another. And this repulsion causes the crystal
Oh, there it is. 2 minutes later.
So if we have an ion structure,
You have two videos going on at the same time. Dr. K.
And who helped me with this? Now we've got to rewind.
Oh, she wrote. Oh my gosh.
and this repulsion causes
Can you
the
turn it up?
crystal to shatter. And that's what causes the brittleness. So if we have a look at an ionic crystal structure with a force applied, once that force is applied, those like charges align and it causes repulsion. The crystal lattice then shatters. Compare that though to a metal structure. When we put on a metal, the cations will move along, but those sieve delocalized electrons will just move around. And this is what makes metal hard but ductile and malleable, whereas an ionic crystal is hard, but it is brittle. It breaks easily. And here's just another representation. So when a force is applied, the like charges line up with each other. You can see here, and they repel each other. The third and last
In any event,
Wait, show me the
Oh, there.
Oh.
are you okay?
Yeah.
Okay, just checking. All right, in any event, you can see the cleavage pattern, and that was a question one year on which the following would represent a cleavage pattern for an ionic compound. I'll try and find the question for you so we can take a look afterward. In any event, what I have done for you here is I have made you a table with molecular and other. So you've got molecular, nonpolar, polar hydrogen bonding, metallic, network, covalent, ionic, and it's got structural particles, so what's in the lattice position, intermolecular forces, typical properties in regard to boiling point and melting point, and examples of all. And I think that will be very good for you as you try and put some of this information together. It is a lot. It requires a lot of explanation. I'm now going to provide you with 40 minutes of practice time. I've got a POGO packet for you that has types of solids on it It requires some thinking. It definitely should be done as a group. And on the back side are alloys. All the answers are on Edline if you want to check as you go. I would work on this today. I'm going to give you your practice quiz as well. And you probably can do quite a bit of it now. The only thing we haven't covered is phase diagrams, which should be review from honors. There are a lot of questions in this packet, but I think it will be very good for you. There's questions on doping, etc. Kids usually find this particular chapter to be a bit tedious. I'm hoping it's a little bit easier as we break it up into smaller chunks. We'll only have about 30 plus minutes on Thursday of new material, and then I'm going to give you time to really work on this. We're going to do the lab on Monday, but we actually should be able to on Thursday to get some in-class time on it to set it up for you with pre-lab, etc. You're looking at a quiz on this chapter next week, okay? It can be a very tricky chapter. Really try and stay on top of it. I'm going to give you a lot of time in class to work on the POGO packet. I'd finish it for next time. Questions?